So did everybody, because I kind of heard some people go, oh yeah. Did, like at the end there, were they kind of just barely moving? Okay. And actually, we're going to have a few more slides. We're going to talk about Galileo, and we're going to see how parallax, actually Galileo used that to his benefit too. So Galileo, yep. So it starts with the letter K. Who was the last person who came up with those 3 laws? Kepler, right. We talked about Kepler last. And so Galileo was after Kepler. One of my last slides on Galileo actually is a sad slide, and it kind of talks about how he ended his life under house arrest. I think he was under house arrest because he died. But there was this tension between, at that time, between the Catholic Church and astronomers, scientists, maybe all scientists, but especially astronomers. So here we have Galileo. So at the time, remember, we're going from having the Earth at the center and the sun orbiting the Earth, which seems kind of strange. That's called a geocentric model, to going to a heliocentric model, where the sun, is where it usually is, where this is the way we know it to be, where this is the sun and the planets orbit the sun. In the plane we call, that starts with letter E, ecliptic. Yep, that'll be on your test somehow. Okay. So one of the things is they're like, okay, and I think I mentioned this the other day, if the Earth is moving, if this is the Earth and we're on the Earth, then anything on the Earth, it's kind of like, have you ever been in a car and somebody takes off and you go, whoa, like if you weren't seat belted in, you'd be back there, okay? So they're kind of like, that's our atmosphere, hello, right? So we'll talk about how he talked about that. The other thing is that, and it kind of goes back to the Earth being perfect. I think Earth is beautiful. And we can talk about by faith again. I don't mind outside of class, but I think it's wonderful. I think the Earth is wonderful. I don't think there's science involved. It's not a mystery. The Earth is not a mystery. Although it kind of is, but it's not. I know, you're right. Oh my goodness. Anyway. So they thought, I know. So you guys told me Kepler. Well, Kepler's first law, starts with letter E, Kepler's first law, says that the planets orbit the sun in shapes called ellipses. Yeah, ellipses. And would you believe, I mean, to me, that's pretty. I mean, kind of flattened. An oval's pretty, but it wasn't perfect, okay? And so they're like, no, we can't have that. And so actually, I'm going to show you here in a minute where Galileo said, well, suck it up. There's other things out there that aren't perfect. And then the other thing is that parallax. The other thing's about parallax. So I'll kind of show you how Galileo addressed that. So Galileo, a lot of times, it's kind of a misconception that Galileo invented the telescope. He did not invent the telescope. He was the first one to use the telescope to magnify celestial objects. Heart sign, right? Yes, heart sign. All right. So the first one, and actually we're going to go into the next part in our lecture. We're going to talk about another scientist, I'm sure you heard of it, is Isaac Newton. We're going to skip a few years. And we're going to see that Newton actually quantified this, but Galileo said that actually, this is the Earth, remember this is the atmosphere, and we got like this, and my atmosphere drops. He said, dude, if your atmosphere has the same speed or velocity as your planet, then your atmosphere is it's going to keep going too. That's called momentum or inertia, okay? So it's like, this has been going on for, 4 billion years. Okay, so the Earth's atmosphere has changed over that time. But my point is that, it's moving too. So that's kind of the deal of that. That's going to be Newton's first law of motion. The thing about being perfect, and I said kind of get over it, remember the whole changing the Earth's orbit from a circle to an ellipse was a big hairy deal. Now, life's full of imperfections. Life's messy. So actually, he used his telescope to look at the moon and said that kind of the moon definitely has what we call blemishes on it. They're beautiful blemishes. Craters, some of you guys saw, and the dark, we call mare, and the White Highlands. It's definitely not homogeneous or perfect. The other thing is Galileo actually saw sunspots on the sun with his telescope. I know, you're like, I'm trying to think. I think he did this by projection. He basically took the light from the sun, magnified so he could blow it up and see the sunspots, and then he put like a piece of paper over here, and you could see the projection of the sun. That's what I'm thinking. The last one was parallax, what you guys just did. The further you got from that pole and that tree, the less, as you moved a whole 10 paces, the less they wiggled, okay? So what he did, and I encouraged all you guys to do this, is he took his telescope, and you can take binoculars and just look at the Milky Way. The darker skies, the better, but even not kind of dark skies, if you know where the Milky Way is, take your binoculars and you'll see all these distant stars. So his point there, and we'll talk about this, why do stars sometimes look really bright, like Sirius, or why do they look really dim, like the stars in the Milky Way? Well, it has to do with their energy output and how far away they are. So he said, dude, those are way far away. And that's why they just kind of look like a fog instead of different individual stars. So he said, you know, if they're very far away like that, this phenomenon of parallax, as the Earth goes around the sun, you're not going to see stars change configurations, change constellations, change patterns, because they're so far away. Okay, they're going to keep their same pattern. The Big Dipper is going to be, look here, the same as it looks over there. So, a little bit more about Galileo. This over here is a famous, now this isn't like a photograph, it's like a figure of what his lab notebook looked like. So for those of you budding scientists, this is his figure. That circle there is the planet Jupiter. And then on either side are these little star-looking things are Jupiter's moons. That's not cool, what? Jupiter has definitely more than 4, but Galileo saw 4 moons.
Just like we did.
Just like we did. We saw 4 moons the other day too. Yeah, exactly. And so Jupiter is the first of 4 gas giants in our solar system. So we have Jupiter, Saturn, Uranus, and Neptune. And all of them have moons. If we look on the inside, let's see, Mercury, no moon. Venus, no moon. Earth, a humongous moon. It's beautiful. And then Mars has 2 moons. They look like potatoes, quite frankly. Only moons that a planet could love. So there is what he saw. The other thing, the thing down here too is Venus. See, Venus is in the morning sky, and I haven't gotten up to see it. I need to do that, to put on my list of things to do. But Venus, this is the deal with Venus. Does this make sense? And this might confuse you, but this is the sun-centered model. Okay, so here we have the Earth, and Venus is inside of the Earth. Inside orbit relative to the Earth. This over here is confusing. If it's confusing, you're right, because actually this would be the geocentric model. This is not the way it is. But with this model over here, I'll go back to Venus. With this model over here, I don't know if you can make it out, but Venus actually would go through phases. It will have its new phase, and then it will be a waxing crescent, first quarter, waxing gibbous, and if it's full, you think we're going to see Jupiter there? No. But, we might see it as it gets farther from the sun, okay? And so this would be a waning gibbous, last quarter, waning crescent, and then it's new. So Venus is so beautiful. Like I said, we'll have to get up in the morning and look for Venus. We'll get out of our little programs and see where it should be. But as the sun rises, you're going to see Venus in the eastern sky right now. My point, keep getting sidetracked, is it goes through these phases. One of the coolest things is Venus. Sometimes you're like, oh, it's so bright, but you put a telescope on it and it looks like a thumbnail. It just is so striking. So that's Venus, and that's a crescent phase. And the reason it can go through phases is because it's just like the moon. We're seeing different illuminated parts of it as it orbits the sun like we orbit the sun. Okay. So I said it was kind of a sad story. There's a book out there, I think written from the perspective of his daughter, and I'm not a reader, but I think it's a good read. So he took a stand with regard to the heliocentric model. Now you might, if you're like me, I'm just thinking, now how come they gave Galileo a hard time, but Kepler went ahead and made 3 laws of planetary motion? So, and I don't have an answer for that. okay? But it's neat when they would publish back in the 1600s that they would actually, they didn't have the internet, so they would like post their little documents on trees and stuff like that. Isn't that, I just think that's, anyway. So yeah, the church banned him. He was exiled to his home, but in 1992, the Catholic Church vindicated. So.
Cool.
I know. So yes, somebody pointed out, I think it was Chloe, that remember it's only 3, is it 3 or 4 of these? I'll grab my thing. I think you guys definitely have it's 3, yeah, choose 3. So like on this original document I handed out, make sure you follow this roadmap. So it's kind of fun reading your answers, which ones you pick. I guess I should say it's fun also seeing which ones you guys pick to answer. Now, when you answer, and in my syllabus it says, I'm looking for complete sentences. Some semesters, I have really been hard-nosed. I'm not an English teacher, but I've been really hard-nosed about complete sentences. But I'm going to try to kind of pull you through that. I'm not necessarily taking off points, but it needs to be legible and try to use complete sentences. You know it's not a complete sentence usually if you start the word with like because. It should, that's a phrase. So again, just keep working it. So let's go on to the next part. So these will be due on Wednesday, right? Okay. Like, not that you really care or anything, but my maiden name was Newton, so there you go. So on to the next part. So you guys told me Kepler came up with 3 laws of how the planets orbit the sun. Kepler, yay, Kepler. And we're going to see that Newton came up with some laws too. But his laws are more general than the motion of planets as they orbit the sun. It makes sense, right? I love science because they kind of build on each other. The one thing that I really think is cool about Kepler and Newton is that their sets of laws, they agree with each other. So they don't like diss each other, and it makes sense. I mean, that's a sign of solid science. Okay. So there he is, Sir Isaac Newton. So Newton came up with more than just the 3 laws of motion we're going to talk about. But in order to talk about the 3 laws of motion, we need to talk about what motion is. So we need to get some terms under our belt. So if you're driving down the road, you say, I'm driving at a speed of 60 miles per hour. Or hopefully you're staying in the speed limit and all that. Okay? So a speed is, if that's what you're going in 60 miles per hour, as I would say, in 1 hour you'll go 60 miles per hour. It's distance divided by time. Well, in understanding motion, we need to introduce another term, and it's velocity. So if you would add to your, I'm going 60 miles per hour, if you would say north, then instead of speed, you have velocity. All velocity does, and to me, velocity is almost a visual thing. I picture a map. All velocity says is you're going a certain speed, what direction? So if you have speed and direction, you have velocity. Then there's some other, 2 more terms we need to talk about. Acceleration or deceleration. Actually, if you're got in your car and you hit the gas, sometimes they call the gas the accelerator, right? Okay. They should call the brake the decelerator. The way scientists handle slowing down like deceleration is it's really negative acceleration. Does that make sense? Yeah. So anyway, acceleration is changing it's changing your velocity, but remember that velocity has the speed and the direction. So these are all examples of changing your speed and or your direction. We look at the first one. The car is accelerating, okay, but going in the same direction. I should say, going faster. I should say, be more generic than saying accelerating. The car is going faster. It starts at 30 and it ends at 60. It's accelerating. But here, notice this car, oh my gosh, he's taking this curve going at 12 kilometers per hour. That might not be so bad as miles per hour, right? But anyway, this car is going the same speed, but changing its direction, okay? One way to think of it is, I'll start with this car over here, and I'm going to draw an arrow right in the middle of the car. And then I'm going to go here, and I'm going to draw an arrow right in the middle of the car, the middle of the car, the middle of the car. Okay, so that arrow is just dead center in the middle of the car. If you compare this arrow with this arrow, can you see how it's changed? It starts out here, and then after it's rounded the curve, it's going like that. Change direction. All right, here's the sun. I am the earth. Okay. Do you see where I am changing direction? Okay. Anything that moves in a circle, even if it keeps the same speed, it's acceleration because it's changing the direction it's going. Okay. So this one is decelerating. It goes from 60 kilometers per hour to 0 kilometers per hour. So deceleration is a type of acceleration. So remember that, acceleration. All right. So Newton's 3 laws of motion. Now again, I already told you that Newton and Kepler don't disagree with this whole planetary motion does not go against what Newton said. This says, and the reason, let's put it this way. If something's in outer space, have you ever heard that it's going to it has the potential, if it's not near any large body, to just go forever and ever and ever and ever? There's nothing to stop it. There's no friction. Now here, like, I'm going to break something one of these days, not on purpose, but here, like, if I drop something, okay, it's going from 0 speed. So it doesn't stay. Here, a better example is, what if I go here, and what happens if I push this? I start it with some force, and I make it go a certain speed, what's going to happen to it? It's just going to stop. Why does it stop? Friction. Yep. There's another force there. I go back to outer space. If we were to do the same thing in outer space, if it's not near any body, it's just going to go forever. What was that? Was it called Gravity? That movie where they got stranded? Okay. Yes. Problematic out in outer space. Okay. So an object will move at a constant velocity unless something else acts on it to change that velocity. All right. So in other words, you guys intuitively told me that if I scoot this, you guys knew it was going to stop, okay? So unless acted upon by another force. So right away, you're like, I knew I made that move, and I knew it stopped. So something else stopped it. So there's other forces at work. All right. This one, Newton's second law. So what does the A stand for here? F is equal to m times A. We just talked about it. Acceleration. Acceleration, yep. Very good. So this says that, I usually look at it this way. I usually say you apply a force, I'll put apply, you apply a force, and it results in some acceleration. I can never spell acceleration, okay? And the acceleration that that object feels is then also a function of its, what does M stand for? Mass, yep. I knew she was going to leave, so. Let's see you Wednesday. So F is equal to ma. Force is equal to mass times acceleration. So you apply a force, your mass will see an acceleration. So what happens if you increase your force? What happens to your acceleration? It increases. You increase your force, you increase your acceleration. What happens if you keep the same force? Now this might be a hard one. We're going to keep the same force, but we're going to increase our mass. What happens to our acceleration? Decrease. It will decrease, right? Because the product of those two will be But don't forget that acceleration, we saw a minute ago, could be something like a car speeding up, a car slowing down, or actually just a car doing this sort of thing. So here we go. Okay, ellipses okay, that's kind of the shape that the planets form with the sun in. That is changing direction of motion, so that is acceleration. So there's some acceleration. Of course, the planets have mass, so there must be some force at work to make this happen. And that's actually going to be the force of gravity, helps kind of tether this whole motion together. So isn't that neat? It's beautiful. Okay, so the first law, we said something in motion will keep that same motion unless acted upon by an outside force. The second one, we said F is equal to ma. That's his second law. His third law says, and I'll kind of summarize it this, you've probably heard it this way, for every action, there is an opposite and equal reaction. Sometimes I think of like when our kids were young, it's like, you hit your brother, you know he's going to hit you back. So that's kind of what we have going on here, right? And there's all sorts of neat little things the way that works. If you're in outer space and if you push off against something, okay, you push this way and it will push you that way. I think of outer space because I kind of like to think of something free floating like that. Okay. This actually is trying to show you the forces, a force and a reaction force by a space shuttle using liquid rocket fuel to basically create the energy to push downward, and it makes, okay, so pushing downward makes the shuttle go up. Okay, very good. So that's his 3 laws of motion. Oops, sorry, go far away. So gravity, I already kind of told you, and we already have a little sense of what gravity is. Gravity, gravity is why when I drop something, gravity is why it falls. Gravity, the force of gravity is also what helps, like I said, kind of keep us tethered, us as the planet Earth, tethered to the sun. Gravity is definitely a player. So here's where, and I'm not a physicist, I'm not an astrophysicist, I'm a chemist, but here's where the whole, how does gravity work? It's not entirely understood how gravity works. It's quantified quite clearly, and this is how gravity works. Okay, the force of gravity, the G actually is some constant associated with this universe. I like to kind of tease, and with another universe it might have a different value. But the big G is something you would look up. The big M's are the masses of the 2 objects that you're trying to evaluate the gravity pull between. Okay? So here we have 2 objects. You could call one the sun, one the planet if you want to. And they have what's called a mutual attraction. Isn't that kind of cool? Because we always think, well, the Earth is attracted to the sun. Well, the sun is also attracted to the Earth. That's kind of fun. So the pull of that, the force of that gravity is that constant G times the 2 masses, whatever the 2 masses would be. Of course, the sun's a lot more massive than the Earth. So that's M1, M2. And what's D? The distance, yep. Intuitively, not looking at this thing, okay, what would happen if I'm not Earth? What if I am that adorable dwarf planet out here, Pluto? I've increased distance quite a bit. Let's just say Pluto has the same mass as Earth, which it doesn't. So what do you think the pull of gravity, did it increase or decrease? It decreased significantly. Yep. In fact, it decreased by a factor of, according to that equation, the square of the distance. So that's a big hairy deal. Well, here's another one for you. Let's go ahead and pick on, what is the planet past Mars? And if you're like, I don't know the order, well, you'll get to know the order. Jupiter, yeah. And did I say you can bring a note card to your, yeah. Yes, you can bring a note card to your exams. And so you might want to put the order of planets, because it'll be on the test somewhere. There's different types of, there's a hard questions, easy questions. Jupiter. So how would you compare Jupiter's mass to the Earth's mass? What do you think? It's a lot bigger. It's a gas giant. Yep. So we're going to take Jupiter, very massive. We're going to move it in at the place of the Earth. So what happens now to the pull of gravity between Jupiter and the Sun? It's more massive. Is it greater? Yeah. It's greater. Yeah. So that's kind of how that works. And I think somebody in here, kind of an initial question, somebody asked about, was it dark matter? Maybe. And actually, we can see the gravitational influence of the mass of dark matter. We can see the influence even though we can't see it. So. All right, so what else we got? Yep, so, on your test, I might ask you kind of just general things like you just told me. If you increase the distance, it decreases gravity. If you increase the mass, it increases the force of gravity between the two objects. Interesting, isn't it? So, who was before Conan? There was David Letterman. So he used to have a lot of ongoing gigs, and one of his things was to drop things off of his roof, go up there and drop it. Okay, I thought that I was remembering it right. Wouldn't you wonder? Yeah, anyway. So I always think of this like this. Now, you can't really gauge how fast something, like if I'm not going to drop again. I don't have so many drops here. So when I drop this, you can't tell, but for the first bit, it will go a certain speed. For the second bit, it will go even faster. So just like this says, for the first second, if we could gauge it, for the first second it falls, it's gonna, the end speed or whatever is gonna be 10 meters per second. We let it go ahead and fall the second, and it will have gone from 10 to 20. And those are just rough numbers. If you take physics, they'll do 9.8, okay? And then if we let it go, if there's room, we let it go for a third second, it'll pick up another 10 meters per second. So it's going faster and faster and faster. And we said if something accelerates, there must be some sort of force making that acceleration occur. And this is the mutual attraction between the mass of this and the mass of the Earth. That's acceleration due to gravity of the Earth. Okay, so it'll go faster and faster like that. Cool. Well, I am going to go ahead and I think pause this because I'm trying to record, but I don't like to record my YouTube videos. So check this out. See what you think. What else we got? Okay, cool. It's weird. So, yeah, in chemistry, we use the term mass and weight interchangeably, but honestly, there's a difference. The mass is kind of more fundamental, and weight is a function of what planet you're on. No, but or what if you're on the moon. The mass, think of the mass as I think of kind of like how much matter something is. And on Wednesday, we're going to get just briefly to all matter is made up of atoms. So we'll kind of talk about the mass that's brought by atoms. That's how much mass something has. And then weight is if you step on a scale. The way scales work is basically they are measuring this force right like that. That's how scales work. It gives you your weight. Okay. So actually, our weight, in physics, they kind of tease out the weight. They tease out the mass from what your scales weigh, the weight. So really, your weight, which you weigh on a balance, is your mass times the force of gravity, the acceleration due to gravity. And I mean, I'm just kind of telling you all that. I don't necessarily, there's a difference. You don't have to do any problems, but there's definitely a difference. So with all of that said, I bet this makes sense since weight is a function of the gravitation between the object that's being weighed and the thing it's standing on, okay, your weight will change, but your mass will not change as you go from place to place. Okay. I mentioned momentum earlier, okay. Momentum, it's I'll say physics thing. You can already see that momentum is another equation. I think they use the symbol P for momentum. Momentum, or P, is equal to mass times velocity. So if you're more massive, you have more momentum. If you're going faster, you have more momentum. I kind of liken it like this. Like if you're going to be hit by, a bike or a Mack truck, both going 30 miles per hour, okay, your Mack truck is going to have a lot more mass than your bike does. So the impact is going to be a lot greater with the Mack truck than the bike. The other thing is if you are a Mack truck or a bike, the whole stopping's a lot easier on the bike, isn't it? Versus stopping on a Mack truck, right? So momentum, it's not an energy, but it's a characteristic function of the mass and the velocity that object is moving. And we're going to see here in a minute that momentum is what we say conserved. Momentum doesn't go away. It can be transferred, but it doesn't go away. So if something wants to change its momentum, we can change its velocity, and we said that a change in velocity is a type of acceleration, or we can change its mass. If we change its velocity, then that must have meant we had to apply a force to make that happen. So let's pick up with this slide. Let's take a running start at it on Wednesday. Okay? Remember that if you're wondering how you can study for this class, I referred to what chapters you want to read in your textbook. Okay? So we can find out. Come on Wednesday. Did you just change his seat?
See ya. I was like, was this like a way to like make sure I'm okay? And she's like, yeah, no, yeah. Diane. And it's on, so with those no electrons.